Thank you, Matt.
Thanks very much, Ross. Unfortunately, we've been going through some very active times for the last 3 or 4 years in New Zealand, and it's certainly given us a lot of experience. So I'm going to talk about some of the work that we've done in the aftershock forecasting and hazard modeling work, and this is work of quite a few people. How do I advance? So just quick overview. Just go through some of the sequences that we've had and the work that we've done for that, specifically the response that we've done for the Canterbury sequence, and then some of the more recent, in the last year and a half, sequences that have been occurring in the Wellington region. A few of the issues that have come up around that, mainly on the communication side, I guess, and then just some additional thoughts on that. So just talking about operational earthquake forecasting in general in New Zealand, we didn't have an active program in this really prior to any of these sequences. We weren't regularly issuing any forecasts. We weren't really doing any at all. However, for probably about 10 years, we've been running off and on internally kind of automated aftershock probability maps, or sorry, tables based on the STEP model. We were running internally within GeoNet for a few years, kind of the same as was done in California, the continuous, regularly updated STEP type maps showing probability of intensity within the next 24 hours. Those weren't really used for anything. They probably actually hadn't been looked at in quite a while. Once they were set up, they weren't going onto the web. What was getting a bit more use was this Epass forecasting, which is looking at a bit longer term than the STEP or ETAS type modeling, and I'll talk more about that in a minute. Those were being used internally, and they'd also were being published in client reports, which is something we have the joy of doing at GNS. Post-Canterbury, we've been kind of in this mode of issuing sequence response forecasts. We haven't really been continuously updating forecasts. We haven't, I guess, more what you would consider operational earthquake forecasting. They haven't been continuous in space and time. They've been focused on the sequence region. I mean, this is similar to work that's been done around the world, I guess, in a number of places now. I think there's some important differences in what we've done, and we've certainly learned a lot through what we've gone through, and there's a lot of improvement we can clearly do. So just as an example, as I mentioned, we put up, I guess these were at least the press in New Zealand was aware of this type of work happening in California, so they wanted these following the Christchurch event. So this was the STEP type map showing the probability of MMI 6 in the next 24 hours. So we put these up very quickly. We had them running already for the whole country, so we put up the Canterbury region one pretty quickly after the Christchurch event occurred. But the response to them wasn't all that great. I think that was, I mean, there's different reasons for that possibly, but there wasn't much familiarity with them. So the media, they weren't all that interested. They did put them into the Christchurch newspaper for a quite length of time, but they weren't what they wanted. They didn't understand them. The maps weren't dynamic enough. They were expecting more changes to happen in them. The public didn't really say much at all about them. So I think if something of this format is where we're headed with things in the OEF space for aftershocks particularly, there's a lot of education required and a lot of thinking on how we do this. And I think if you go to Ann Wine's talk on Friday, she's been involved in a study where they've done a lot of looking into the understanding of the information that was going out during the Christchurch sequence, and has a lot of good thoughts on that. So on to the kind of the bulk of what we did following Canterbury, and Christchurch and the whole Canterbury region is a low to moderate hazard level in the seismic hazard model for New Zealand. So it was pretty clear straight away that the expectation of aftershocks was going to exceed what was in the building codes for that region. So we went on to a program to kind of develop a time-dependent model based on existing work to see if the building code should indeed be revised, and that's what happened. There was about a 35% increase in the building design standard for the region. So this is based on a long-term forecast, on a 50-year forecast. Now this is by no means finished, but that's where things are now. And just quickly, what we did in that, it was not just a standard aftershock forecast for this. We had three different components that went into that. There's the short-term clustering component, and this is based on a STEP and an ETAS model, so this the standard aftershock modeling. and then into the medium-term component, and this is really based on the Epass model, which I'll talk about in a minute. And then a kind of what's actually turned out to be a very important component of this model was where we were headed to in 50 years, and that's the long-term seismicity component. Now, all the models that we used in this hybrid model, as we're calling it, were models that were already under testing within the CSEP testing center in New Zealand, and many of them were being tested elsewhere around the world. And retrospective testing now within the CSEP environment shows that this ensemble that was put together outperforms any of the individual models on their own in this retrospective testing, so that was quite good to see. And just as an example, I can't see it very well from over here, hopefully you can see it a bit better, but this breaks down the short term, the medium term, and the long term components into different magnitude ranges. So this is magnitude 6 to 6.9, and the really quickly dropping off component, that's the short term component, the aftershock component. This other component here, that's the medium-term component coming from Epass, and then here's the long-term time-independent component, and it's the three of these that get combined together to provide the longer-term forecast. So now just a bit more about the Epass model. It's quite a complicated model to get your head around, so I'll just get a quick overview of that. Again, this is really looking at the medium term. It has some similarities to the ETAS model in that every earthquake that occurs in the region has some contribution to the probability of future earthquakes in that region, but really looking at longer term clustering. It's based on kind of three fundamental empirical scaling laws that are related to what's called a precursory magnitude. And this has come out of work that David Rhoades and Frank Evison were doing for probably more than 20 years now. Basically looking at a summary sort of magnitude for a region, and then you get a scaling with that for the expected magnitude, so that it's not a Gutenberg-Richter, it's some distribution of larger magnitudes based on that. It scales with the time, so the larger the precursory magnitude, the further away in time that the next event is expected to occur, and then the area scales up with that precursory magnitude as well. And it's really looking at the longer term, or I guess medium term in this case, as I said, looking at the 2 to 25 year range. And this has been tested globally, both in and outside of the CSEP environment, and I think it's probably one of the more tested models out there, and it does show significant skill in its forecasting ability. And I think there's been some debate about whether this is kind of just a subcomponent of what's already represented in ETAS, and David Rhoades has certainly been an advocate that it is a different phenomenon than what's seen in ETAS, and I think possibly some recent work from David and from Morgan Page is kind of indicating that maybe that is correct, that it's showing scaling laws that you don't necessarily see in the same way in ETAS. And then the long-term component, and this is particularly important in Canterbury for two reasons. One, this was a very low seismicity region prior to all this, so there were almost no events there to do, say, a smooth seismicity model based on. And two, Epass is very much like ETAS in that you need to do simulations to get the full range of expectation. It really just gives the first generation of events, and currently that's not possible, so this is really trying to take account of that. And this is really one of the more contentious parts of what we actually did, and it turns out to be very important to where this 50-year forecast is headed, is where do we expect it to be in 20 or 30 years or 50 years? There's lots of different models of what this could possibly be. Everybody has different ideas on how the data should be prepared, whether or not the catalog should be declustered in this case, how far back in time you should go to do this, and all this has a significant bearing on what the long-term rate is. So I think this is a really interesting problem, and one that I think a lot of us don't necessarily put as much emphasis into as we could when we're developing our short-term models, is what actually is that background component. So now onto a few of the communication issues that we ran into with this long-term model, this time-dependent model. It really came down to inexperience with time-dependent models on the end user's parts. One of the key ones that I've been harping on a little bit now, which has caused a lot of difficulties for us in the application of this model, and that's the use of return periods, where we're talking about instead of a 10% 50-year, where we're actually talking about an uncertainty on a given rate that gets converted into a return period. And that's not actually correct, particularly when you're moving into a time-dependent model. And that's led to a lot of inappropriate use of these results that we're putting out by people that don't understand the difference between this return period and an uncertainty on a shorter-term rate. how to communicate the temporal decay in useful terms to decision makers. So they're trying to make long-term decisions based on a rate that's on a model that's decaying in time. So how do we get them to understand that best? And how do we do this all under time pressures? So having all this stuff thought out ahead of time. I'm gonna have problems moving forward. I'm possibly being a little bit cynical in this one, but this is actually one that's hitting a bit close to home right now. And I think when we move out of the space where we're just providing the forecast, where these are actually into the applied world where they're getting used, and that we'll start to work with people who are they have to make decisions with incomplete information. And I say gut feeling, you can call it whatever you want, but I guess they need to make decisions when as I say, they don't have complete information, and that leads to much more subjectivity in how things are done, and that's led to some difficulties here, primarily in the disbelief of the forecast and also of the tests that the forecast have been put to. And one of the main things that we're seeing now is that it's quieter now in Christchurch, as you would expect. The aftershocks are happening much more infrequently. So we're hearing a lot of statements now that the sequence is over. We need to adjust our models down. We need to change to adapt to this. And that's causing difficulty in how you communicate the clustering nature of aftershocks, and that we don't expect a uniform rate of earthquake, uniform decay in time, that we expect clusters to be seen. There's also very much a perceived lack of relevance of the importance of the CSEP style testing. I might skip this one. I've shown this one a few times now, but I seem to be going a bit long, so I'll just go on to the next, and that's we've had now, I guess, 3 M6.5 and greater in the Wellington region in the last year, so we've gone through some of these exercises again. We've shown the same sort of probability tables where we show the expectations of events and compare those to what's actually been observed. There's continued to be this reluctance both from kind of officials and also from the scientists themselves to produce the probabilities for the larger events, so that we are getting those out there now with some difficulties. But I think one of the main things that we've done differently is we moved into adding these probabilistic scenarios both to the public and to the government. And what these are, I don't expect you to get all the details here, but these are really giving context around the probabilities that we are providing in the aftershock sense. So this is taking into account the geological environment, what the faults we know of are there, the relativity to the subduction zone. So these are all these events have been occurring directly above the Hikurangi subduction. So it's done in a much more subjective fashion, but very much controlled by those probabilities that are coming out of the aftershock modeling, just to give a bit more understanding to those who are needing to make decisions about what these probabilities could actually mean. These have been, I guess, very well received by the public and by the decision makers, and they've been requested, in fact, to have these. And it's been very informal how we've done it at this point. We've been lucky in how just in the situation where the events have been, we had a lot of knowledge, and an overriding goal is that it must be consistent with the the aftershock probabilities. We're now working on how we can formalize this procedure a bit more, where it's been done in a pretty ad hoc manner so far, and how should we do this? Who are the right people to be involved? What other information do we know about the regions that we can contribute to this? And I think an important one is when we're making these sort of decisions under pressure, how do we best communicate the actual knowledge that we have, and how do we kind of avoid overconfidence in what we know, so we're just putting out the best information that we can. So just in conclusions, government and society interest has really driven our work to be focused on the medium-term and the long-term forecasting much more than we ever expected it to be. So it's really changed the focus of a lot of our work. And there's really been this strong appetite for us to provide our best scientific judgment, and that's really in these scenarios, even when it's not fully quantifiable, that we can put it into the context of what we have, but they want to know a little bit more than just these fairly simple aftershock probability type things that were given out. So where are we headed with this? Much more learning from the work like what Ann Wine will be talking about, and other activities that are going on, and much more interaction, I think, with the social science community as we're moving forward with this aftershock type work. We're currently working on our next revision of our national seismic hazard model for New Zealand, And an important component of this will be a time-dependent component where we're really trying to go from the short-term, medium-term through to the long-term, because there's a whole range of end users out there that need different levels of information, so we want a continuous way to do that. And then formalization of the scenario procedure. And then just final question I wanted to throw out there that I don't necessarily know the right answer, I don't have a strong opinion on the right answer, but I think it's worth some discussion, and that's just purely in the applied sense, not in the more fundamental research sense. How useful is continued refinement of these short-term aftershock models? How much more I think we can tinker with them forever, but how much more information gain are we really going to get in these standard aftershock models, and what are the areas in terms of forecasting that we need a bit more effort? And I have my thoughts on that, and I certainly think it's interesting for more discussion. Thank you.